Hello, grade 12s. Welcome to this physical science lesson. My name is Gillian. Today, we're going to consolidate our knowledge of change in momentum and impulse. Now, I know we didn't cover impulse to a large extent last time, so we're going to revise it before we get into the nitty-gritty of the questions. Okay, so let's remind ourselves. Impulse is the same as change in momentum. It is the force, net force, exerted over a period of time or a change in time interval. So you may have seen the simulation where we drop eggs. The egg is the same size, same mass, and it is dropped onto different surfaces. So if it falls onto a hard surface like tiles, you can imagine it's going to splatter everywhere. But if we change that surface to a softer surface like sponge or material where there's a bit of give, what we do is we change the time period for which the force is acting. So the egg doesn't change, it stays the size it is, it stays its mass. Its velocity is the same because we are just dropping it. We're not throwing it, we're just dropping it. So its velocity is the same. But when it hits the softer material, it takes a longer time to stop. And so the force is not as dramatic and it is less likely to break. And so that's what we find with impulse. So that is impulse. It is if we change the time of that change in momentum, the force is going to change too. So let's look at the screen and we see that we have got the net force times the change in time, and that is what we call impulse. So when we write, when we're solving for problems and we're writing, we need to write the word impulse. So we write impulse equals F net times, you can put a dot, the change in time. Now that is the impulse, which is the same as the change in momentum. Impulse does not have a symbol. That is why we need to use the word impulse. You need to write it there, impulse. It has strange units. It has these units here, which are Newton seconds. Be careful. We tend to write to the minus, so we tend to write Newton per second. It's not per second. It's a Newton times a second, so Newton second. Okay, now because we are dealing with vectors, we have to speak about direction. So the direction of the impulse is the same, it's equal to the direction of the change in momentum, which is the same as the direction of the net force, if you remember back to momentum or change in momentum. Now, when we have objects that are in contact with one another, so whether it is the egg in contact with the material, whether it is the squash ball or the tennis ball in contact with the racket, at that time that they are in contact with one another, there are things that they are going to share, values that they are going to share. So when they are in contact with one another, the one value that they are going to share is the amount of time that they are in contact with one another. That makes sense, right? So they're in contact with one another for a certain period of time, and then they move away. Whichever way they move, they are going to have the same time for contact. So objects in contact have the same amount of time. The other thing that is the same that is the net force. So the net force that they experience will be the same. Now, we remember Newton's third law, and that's exactly it. So the one body A will exert a force on body B. Body B will exert the same force on body A. However, it is only the same in magnitude. Magnitude, how big it is. The direction is different, and that's key to note. So the forces that they experience will be the same in magnitude, but opposite in direction. So one we will say as positive. So if it's A, it will be positive direction. B will be in the opposite direction. So we will say that its net force will be in the negative direction. I gave you a picture of a golf ball being hit, just to show you how a change in momentum can be seen at a split-second level. So you can see that ball would have been round, a force has been exerted on it, and it is now squashed flat. So, well, flattish. It has actually changed its shape. So that is an example of a net force being able to change the shape of an object, and that would have happened in the moment of contact between the golf ball and the golf club. That's where we have an impulse. Now, for the impulse, we see a really important relationship, and that is that the net force is inversely proportional to the time. And so that means if we increase the time, the force is going to have to decrease in magnitude. If we shorten the time, if we make the time smaller, then the net force will increase. So in accidents or in cars where there is possibility to get injured, the physicists try to lengthen the time. So the seat belt and the car crumbling in the front are all designed to lengthen the time of impact so that the force will be less on the people involved, and therefore the injuries will be less. Let's move on to our first question. So we have a tennis ball of mass 200 grams. It is moving with a velocity of 20 meters per second. It is hit by a racket. The ball moves off in the opposite direction with a velocity of 15 meters per second. The racket is in contact with the ball for 0.3 seconds. So my mind goes, lots of information, let's draw a picture. Just for me, doesn't have to be a work of art. So a tennis ball, and its mass is going to be 0.2 kilogram. How do I get there? I divide 200 by 1,000. To convert grams to kilograms, it is moving in one direction, and that is at 20 meters per second. I'm going to call that direction positive. So that is the positive direction, and you could call that negative, it's up to you, but I'm going to call it positive. It is the first direction that is given to me, so I'll call it positive. What is happening? Well, a racket comes along. I don't know how well I'm going to draw this racket. Someone with a racket hits that ball, there is a collision, the two collide, there is contact with the racket and with the ball, and the ball then moves off in the opposite direction. And that is then a negative direction. I'm going to call it negative, and at 15 meters per second. So this isn't quite correct, this drawing, because I've drawn the two arrows the same. So ideally I would have drawn it a little bit smaller. This contact would be 0.03 seconds in time. What are they asking me? Calculate the momentum of the ball before it is hit. We can do this. So momentum is equal to the mass of the object times by the velocity of the object. The mass of the object is 0.2. The velocity is in my positive direction, remember? So positive, I think it was 20. Let's check. Yes, there we go, 20 meters per second. I haul out my calculator and I get an answer of 4 kilograms meters per second. We need a direction for this, and we're going to say in the positive direction. Okay. Next question. That was cool. Next question. Calculate the momentum of the ball after it is hit. Okay, so again, P is equal to mv. The mass is 0.2. Now we need to be careful. The velocity is in the opposite direction, so it will be negative. Negative 15. My answer here when I work this out is minus 3 kilograms meters per second. I cannot leave it like this. I need to say that this is 3 kilogram meters per second in the opposite direction. I could say in the negative direction too. What is our next question? Our next question says, what is the change in momentum of the ball? Okay, so we need to work out delta P, change in momentum. How does this look for us? What do we know about it? Well, we know that it would be the final velocity minus, sorry, not velocity, the final momentum minus the initial momentum. Do we have those values? Yes, we do, because we have calculated them. So what is our final momentum? If we go back to our slide, we see that it was negative 3 kilograms meters per second. Why would we want to put in that negative? It's important for direction. Change in momentum has a direction, momentum has a direction, and so we would need to put in the negative direction, the minus direction for the final momentum. So that was minus 3, and now we're going to minus the initial momentum, which was a value of 4. And we end up with a value of negative 7 kilogram meters per second. We can't leave it like that, so we need to write that this is 7 kilogram meters per second, and that is in the opposite direction, or we could write in the negative direction. Right, grade 12, so we're going to take a quick break, and when you come back, we're going to finish this question. Welcome back, grade 12s. We're busy with momentum and impulse and change in momentum, and we're going to continue with the question that we were on. So we've got a tennis ball, it's 200 grams, it's been hit in the opposite direction, and we have just calculated the change in its momentum. Right. What is the next question? What is the impulse exerted by the racket on the ball? Okay, impulse, let's think about impulse. Impulse is about the resultant force or the net force acting over a period of time. Okay, so impulse, we're going to write the word impulse. The reason is because impulse does not have a symbol. So we write impulse equals, and what is its equation? Well, it's the net force times by the change in time. We also know that this is the same as the change in momentum. How is that? That's awesome. We have just worked out the change in momentum, haven't we? So we can say that it is exactly the same. Are they asking us for impulse? Yes, they're asking us for impulse. So We know that the change in momentum is -7 kilogram meters per second. Why the negative? Because of the direction. That means that the impulse must be exactly the same. So this is then equal to -7. We can't use kilogram meters per second. That is the unit for change in momentum. What are the units for impulse? They are Newton seconds. So we're going to do this. We're going to write Newton seconds, and that's going to be 7 Newton seconds. In which direction? In the direction of the change in momentum, and that will be in the opposite direction. That was much easier than I thought it was going to be. If we just think through things, it doesn't seem so overwhelming. Next question. Oh, calculate the force exerted by the racket on the ball. Okay, so now we need to think, where do we have an equation that's got the net force in it? We have just used it. So we have just used impulse equals the net force times by the change in time. And we know that that equals the change in momentum. We have to calculate this, the net force. Okay, we can do this. Net force, that is what we have to calculate. What is the change in time? We were told it's 0.03 seconds. What is the answer? Well, change in momentum is -7, and we know that the impulse is the same. It's -7. To rearrange this, we are going to divide by 0.03 on the one side, and therefore we've got to divide by 0.03 on the other, and we end up with an answer of -233,33 recurring Newton. We can't leave it like that. So I'm just going to move up here. I'm running out of space, and we're going to write this as F net equals 233,33 recurring newtons. What does the negative tell us? In the opposite direction. Cool beans. Excellent. Let's move on. What would you expect to happen if the racket was in contact with the ball for 0.05 seconds? Now, initially, it was 0.03 seconds. Now they're asking 0.05 seconds. What would you expect? Are they asking us to work it out? No, not necessarily, because they don't say calculate. But this is a reasoning question, because they're asking you your opinion. So what would we say? Well, we know that the net force is inversely proportional to the change in time. Because, why are we saying that? Well, we're saying that the change in momentum must be the same for a particular situation. So the change in momentum, or the impulse, so the impulse must be the same for this particular situation. So what is going to happen? How must the values change to accommodate this? If we have an increase in the time, then the net force must decrease to maintain the constant change in momentum. So we must have a decrease in this force, the net force. So what can we say about this? How are we going to write this? This is how we're going to do it. We're going to say, you expect the net force to decrease. So expect, I'm running out of space, so I'm not going to write in full sentences. Expect the net force to decrease. Or you could write to get smaller. And why would it decrease? We need to say why. Well, we're going to say that the net force is inversely proportional to the time taken. Therefore, let's do it over here. Therefore, if time increases, net force must decrease. Okay, I hope you're happy with it. That's a good answer. I like that answer. Okay, let's continue. We have another question. We've got ball P of mass 0.16 kilograms. We're lucky, we've been given it in kilograms. Moving east, that's interesting. So now they're giving us a direction and a speed of 10 meters per second. It collides head on, so we have a collision, with another ball Q with a mass of 0.2 kilograms. It's moving west, so it's moving in the opposite direction at a speed of 15 meters per second. After the collision, ball P moves west at a speed of 5 meters per second, as shown in the diagram. I'm very relieved there's a diagram because it's quite confusing, and if there wasn't, I would draw myself one. So it's telling us to ignore the effects of friction and rotational effects of the ball. So what it's telling us is we've got an isolated system here. We're ignoring all the external forces. So let's have a look at this diagram and see if it makes sense to us. So we've got ball P, here it is ball P, and ball P is moving in the easterly direction. So it's moving east. They've been kind enough to give us some directions here. And there, a compass, there we see that east is in that direction. Excellent. It is moving with an initial velocity, so that's its initial velocity, of 10 meters per second. Now, it also has a mass, and the mass is 0.16 kilograms. We just write that in. We have got ball Q. Ball Q has a mass of 0.2 kilograms, so it is slightly heavier. And it's traveling west, and it's traveling at a larger velocity. Can you see there? 15 meters per second. They have a crash. Here's our crash. And P bounces off in the opposite direction. So now it is going west. It's going west, and you can see that its final velocity is a little less. Okay, I think we've got that. You can picture that, right? Now they're going to ask us a question. So calculate the magnitude of the impulse on the ball during the collision. So we've got these two balls, they crash into each other, and then P moves in the opposite direction. There's an impulse. When they connect, there is a time that they are together, there is a change in momentum, and obviously there is a net force that is exerted to change that momentum. So we need to calculate this impulse. So let's move on. So we've got some space. Impulse, what do we know about impulse? Let's write the word impulse. We know that it has no symbol. We know that it is the net force times by the change in time. What is that equal to? We know that that is equal to a change in momentum. Okay, so we've got that. Now, let's see what information we've got. We're talking about the impulse on ball P. That's what they're asking, ball P. We are then going to look at the data, the information that's been given to us about ball P. We know its mass. Its mass is 0.16 kilograms. We know that its initial velocity is 10 meters per second. I'm going to call that direction positive. Okay, so that was the east, easterly direction. That's the direction. I'm going to call that positive. What about the final velocity? The final velocity is in the opposite direction. We see it as being 5. It is 5 meters per second, and I'm going to say that it is negative. Why? Because it is in the westerly direction, and that is the opposite direction. Is there anything else that we know? I think we've got it all. So now let's see if we can work out the impulse. We don't know what the force is. We don't know that. We don't know what the time is. No. So we can't use that part of our equation. We're going to have to use the change in momentum. So change in momentum is, we know the mass stays constant. Final velocity, subtract initial velocity. The mass is going to be 0.16. Final velocity is -5. Initial velocity is 10. And if we calculate that, I hope you're noticing that we have got negatives there. That's going to give us a negative answer of -2,4 kilogram meter per second. Okay, what does that mean? That means that we have got 2,4. Now, careful. This is the change in momentum, but they're asking me for the impulse. So the impulse has a different unit. An impulse is Newton second. It's negative, which means it is west. Right, grade 12. That is all we've got time for, unfortunately, today, because there's so many more exciting questions to go through. Please check the online school. There will be questions there with answers that you can practice, because this is all about practice. Okay, I hope to see you next week.